All right, we're going to come back to exponential growth, and we're also going to look at the doubling time. So let's say exponential growth models and doubling time. So what I wanted to do is actually, let's just explore, I was going to say example, but let's just explore this idea. Let's start off with this function y equals 2 to the x. In many ways, I think, at least for talking about exponents and functions and explaining what's going on, I think this is a really good one to work with. But for reasons that involve calculus, we like to use base e, and e is between 2 and 3. But let's just go ahead and put 1 here, and then I have 2 to the 1 power is 2, so what I'm doing is making a little table. And so okay, so this function is doubling. I left room to put in -1 and -2, but now I thought, oh, do I really need that? I guess I could do that just to make this complete. But usually we start at time 0, so it's not really all that relevant what happens before then. Okay, so what we see is we progress as t increases by 1, y doubles. And so what we say is that the 1 is the doubling time. And you can really see that when we have this base 2 exponential function. All right, now I just want to tweak this a little bit. Let's put a bullet on that one. And now let's look at y equals 2, but I'm going to look at x over 3. And I'm going to make a graph and a plot and all that stuff. And so look at 0. 2 to the 0 over 3 is just 2 to the 0, and that's 1. Now, instead of putting in 1 next, I'm going to put in 3. Why won't I put in 1? Because 2 to the 1/3 is something that we'd have to use a calculator to figure out, or to get an approximation. So I'm going to put in 3, because then I get 2 to the 3 over 3, which is 2 to the 1, which is 2. And then if I put in 6, I'll get 6 over 2. So do you see, 6 over 3. So see, what I'm trying to do is I'm trying to get multiples of 3 that I put in there. And the reason is then I can just do this in my head and make a good point that I'm trying to show here. So this is all exploratory explanation. Okay, so now this one still starts at 1. The one above also started at 1. Okay, so this starts at 1. But how far do I have to go until it doubles? It starts at 1 and 0, but then I have to, it's going to take a little longer to double, 3. And it seems that unfortunately maybe I didn't plan this all that well. Well, no, it's all right. Okay. So then it doubles to 2, and then 2 doubles to 4. So this doubles when t, or x, increases by 3. All right, so you see how that works? When I go from 3 to 6, I go to 2 to 4. When I go to 6 to 9, I'm increasing. This is, plus 3. Over here, when I add 3 each time as x increases, but what happens to y? I don't add 3, I multiply by 2. That's what's happening with y. All right, now, in general, let's just look at, not quite general yet. Now let's look at y equals 2 to the x over d. This function doubles when x increases by adding d. So it's, you know, the same reasoning as we have above here. It makes it more abstract to put d instead of a number. And by the way, I'm gonna make sure that I wrote the d is greater than 0. I don't know, maybe something would happen when it's negative, but let's have it greater than 0. So I have 0, and then I get 2 to the 0 over d. That's 2 to the 0 is 1. And then I'll put in d. So d is some positive number, and I get 2 to the d over d, which is 2 to the 1, which is 2. So see how I'm doubling? I add another d, and I get 2d. That makes 2 squared is 4. 3d, 2 to the 3d over d, that makes 2 cubed, and that's 8. So d, 2d, 3d, and there we go. This is 0, 1, and this is y equals 2 to the x over d. Okay, now let's make this even more general and write y equals a 0 to x over d. Oops, well, that didn't look so good. Oh gosh. Y equals a0 to x over d. D is greater than 0. All right, so what's going to happen here is if I put x and y, if I have 0, I have a0, 2 to the 0 over d. So that's a0 times 1, which is a0. So that's our starting amount, our starting population. And then I'll put in 1, and I have a0, 2 to the, no, let's don't put in 1, put in d. 2 to, a to the d over, 2 to the d over d, that makes a0, 2, so it's, you know, it's 2a0. Then I'll put 2d, and I'll get a0, 2 to the 2d over d, which gives a0, 2 squared, which makes 4a0. So this is doubling every d. All right, so what do we see here is that the graph looks like this. We start off at 0, a0, and it's going to double to, so here's a0, then it's going to go to 2a0, and then doubles again to, so that's 1, 2. Well, okay, I don't know what, I'm just getting a little bit worked up. Okay, so 2, okay, this is 1a0, 2a0, 4a0 would be here. All right, so then we have d, 2d. All right, we can keep going. 5, 6, 7, 8. Well, I made a lot of mistakes that wouldn't look that bad if I had an eraser, but I'm using pen. So here we start at a0. After time d, it goes to 2a0. At 2d, we get to 4a0, and then 3d, 8a0. So it's doubling each time. Y doubles as we progress. So a0 is the amount at t equals 0. D is the doubling time. And the doubling time is the time it takes for y to double. All right? And then the thing is, I'm sort of switching between x and y, so I don't mean it at t equals 0, but at x equals 0, which I can still call time. So maybe the whole thing would have been better if I used t instead of x throughout. All right. Okay, so let's look at, we can write a equals a0 2 to the t over d. T is time. A0 is the amount when t equals 0. D is the doubling time. All right, this all looks pretty good, but for calculus reasons, we don't like base 2. So why am I using base 2? So I can explain this. That's why I'm using base 2. But I want to show you something which is like a little slick trick here, is that note that we have this fact is that e to the ln of 2 is equal to 2. Why? Because of a cancellation property when I have a composition of inverse functions, e and ln, exponential and ln. Okay, so those cancel out. We have from above a equals a0 to the t over d. So I can swap out for 2 e to the ln 2. Why would I do that? Simply because I like to have base e when I'm using exponential equations. And why? We need to take calculus to see that. But anyway, we're just going to believe that for now. So what I'm going to do is I'm going to multiply this, because that's the rule when I raise to an exponent. And I'm going to multiply ln2 times 1 over d. And I'm going to get ln2 over d to the t power. This is all raised as an exponent. You could write a equals a0 exp for exponent ln2 over d times t. Sometimes you see in papers, like science papers, when they have a huge amount of stuff in the exponents, they don't write e to that power, they write exp. But this is our general rule for exponential growth. Exponential growth in general is given by a equals a0 e to the kt, but as we see, k is equal to ln2 over d, where d is the doubling time. D is greater than 0. A0 is the amount at t equals 0. All right, so what's the point of this? The point of this is we have this equation refined a little bit more. And what was all that buildup? That was all explaining that equation. And some people might have just want to fast forward the video, get to this point here, or just see. But this is the deal. Exponential growth is a equals a0 e to the kt, t is time. But k can be expressed as ln2 divided by d, where d is the doubling time. Now I can write over here, t is time. Okay.